Okay, so in this part of the lecture, I'm going to talk about the fast Fourier transform. And so back in 1965, two guys, Cooley and Tukey, recognized a shortcut in computing the discrete Fourier transform that reduced the complexity. And so that's what I'll go through in this lecture. Just to talk about the complexity of what we've learned so far in the discrete Fourier transform, notice that if we just have this case where n equals 4, and if we compute y, notice that if we take our vector x and multiply the first row of our Fourier matrix, there are 4 multiplications, and then there are 3 additions. And if we continued with multiplying our vector x by the second row, the third row, and the fourth row, basically we end up getting a complexity of n squared for the discrete Fourier transform. So I'm going to first write down that in order to do this analysis for the fast Fourier transform, I'm going to write y as 1 over root n z. This will make our computations easier. And so here I'll note that the discrete Fourier transform has complexity. That is on the order of n squared. Okay, there are n squared multiplications, and then there's going to be n times n minus 1 additions. Alright, so to go through the details of the fast Fourier transform, recall that I've labeled y as 1 over root n z, so we get rid of the 1 over root n, and I'm going to write the components of z. z0 is equal to omega 0 x sub 0 plus omega 0 x sub 1 plus omega to the 0 x sub 2 plus omega to the 0 x sub 3. And so continuing, I have z1, z2, and z3 written as a linear combination of x0, x1, x2, and x3. And so now I'm going to note a few things about our omega being raised to various powers. Note that omega to the 0 equals omega to the 4th, which equals omega to the 8th. And also omega squared equals omega to the 6th power. And so what I'm going to do is I'm going to insert omega 0 whenever appropriate and omega squared whenever appropriate. And notice that the order of the linear combination is x0 term, x1 term, x2 term, x3 term. I'm going to switch the x1 and the x2, and I'm going to group things in a certain way that will be convenient. Okay, so now you see how I've grouped the x0 terms and the x2 terms together and have used the properties just previously mentioned, and the x1 and the x3 terms so that we have our z0 through z3 written in this manner. And so now what I'm going to do is I'm going to so notice in parentheses, the only things that show up are omega to the 0 and an omega squared. So I'm going to let mu equal omega squared, and I'm going to let u0 equal mu to the 0 x0 plus mu to the 0 x sub 2 and then I'm going to let v0 equal mu to the 0 x1 plus mu to the 0 x3, and then u sub 1, so I'm constructing two vectors u and v both with 2 entries, and so u sub 1 I'm going to let equal mu to the 0 x sub 0 plus mu to the 1, remember mu is omega squared, u to the 1 x sub 2, and v1 equal to mu to the 0 x1 plus mu to the 1 x sub 3. So now, in terms of u and v, z0 equals u0 plus omega to the 0 v0. Of course, omega to the 0 is just 1. Z sub 1 is equal to u sub 1 plus omega to the 0 v1 and z sub 2 equals u sub 0 plus omega squared v sub 0. And so let me catch a mistake here. The exponent in z1 of omega here is a 1. Okay. And z3 equals u sub 1 plus omega cubed v sub 1. So now, notice that in how we defined u is actually equal to m2. Okay, remember what I called m sub 4. It was the Fourier matrix without the 1 over root n term. So m sub 2 is the Fourier matrix, 2 by 2 Fourier matrix without the 1 over root n term. Okay, so u is equal to m sub 2 x0 times x2, and v is equal to m2 times x1 x3. So to compute this discrete Fourier transform using this idea, notice that there are, we basically compute two DFTs of 2 by 2 matrices, so I'm going to write it this way, and then plus a computation of z, which is going to require 3 multiplications and 4 additions, and hopefully you see that. So in this case, I'm just going to write, I'll just add the 7 and then we'll generalize. So if you look at z, the omega, so you see the product of the omega to a certain power times the v components of v. There's really only 3 multiplications because omega to the 0 is 1, and then we're just doing 4 additions. Okay, we're going to compare this to doing a discrete Fourier transform of a 4 by 4. So now we're going to compare to discrete Fourier transform of a 4 by 4. And in the notation, the DFT of 2 just means that you're doing the computations that are involved for a discrete Fourier transform of a 2 by 2 using the normal way. So now I'm going to do an analysis of the complexity of this fast Fourier transform compared to just doing an ordinary discrete Fourier transform for a matrix. So, in general, I'm going to let 2 to the m equal n. Okay, so we have an n by n matrix. Imagine that it can be written in the form of 2 to the m. So the count of a DFT of a matrix of a size 2 to the m equals, so we do 2 times the count of a DFT. See, that's basically of half the size. So a DFT of size 2 to the m minus 1, and then plus. So if you recall, in the case of a 4x4, we did 3 multiplications and 4 additions, and so if we generalize that, it would be 2 times n minus 1, or in this case 2 times 2 to the m minus 1. And so now we can sort of inductively argue that the DFT of a matrix of size 2 to the m minus 1, we can substitute in for the DFT of 2 to the m minus 1. So this equals 2 times the count of a DFT of order 2 to the m minus 2, and then plus 2 times 2 to the m minus 1, and then plus 2 times 2 to the m minus 1. And so I think I'm missing a bracket here, so let me, yeah, I'm missing a bracket here, all right? So if we continue with this, we would be able to determine that the count of doing a DFT of a size matrix 2 to the m is going to equal 2 to the m times 2m minus 1 plus 1. This would be the number of operations if we use this fast Fourier transform. And since 2 to the m equals n, we also have that m equals log base 2 of n. And so if we substitute this in, so this is sort of an aside, then our count is going to equal n times 2 times log base 2n minus 1 and then plus 1. So what's the order count for a fast Fourier transform? The fast Fourier transform has complexity. That is on the order of n times log n, which is better than n squared. So the fast Fourier transform is computationally more efficient.